Hi, and welcome back. So, in the first video of this series that I'm planning to present for you, which is about transmission lines, I started introducing the content of the transmission line design handbook from Brian C. Walton. We started looking at the structure of a transmission line on the page 10, figure 2.1.1, which is this one that you are seeing right here, which I told you that is a structure that can represent both a coaxial cable or a microstrip line. This last one is our goal on this series, since we are interested in microstrip lines printed in substrates. Now, in the second video, I want to make a quick revision of the first one, so we can go on to the end of the exercise and finding the characteristic impedance is zero, which is the primary objective. Remember, we want to control the amount of current that are being feeding between components that are interligated by these microstrip lines, and the impedance is responsible for this. Okay, so in the first video we finished with these equations right here, which represent these individual sections of the structure. Of the networks, or partitions, better saying. And they were modulated taking consideration the way that the RLC elements behaves under the electromagnetic fields, which is these equations which represent each of these elements. What I do not tell to you is that there's no real RLC components in the network, and it's important to make this clear. Is just the way that they behave, and we are using all this physical theory to modulate these microstrip wires printed in substrates. Right now, we will not get in substrate theory, which basic involves the concept of permeability and conductivity, which is crucial for the way that the electromagnetic fields will be contained and contained on the dielectric, and this is also influences the end impedance. What I also don't mention is that that is a primary a wave propagation problem, since we are dealing with the variation of V and I on the network, and this explains why we are using the operator of partial differential equation, since there's these two variables. Okay, so let's start the part 2, building a strong knowledge about the difference between differential and difference. The handbook that we are using points to us that is being replacing differences with differentials by taking the limit as delta y approach to 0, and this way we can write these equations. We worked these equations, taking this in consideration on the first video, replacing differences by differentials. And this way we are capable to write these equations for a given signal on the infinitesimal section, taking delta y and taking here to 0. Delta y is the operator that represents the infinitesimal section, and in calculus is the result of subtracting one quantity from another, which we call the operation of difference. And as you can see, this gives us an infinite changes of values, as you can see. In the other hand, we have the differential, which by definition is an infinitesimal change in the variable. What these equations are telling to us is each section of partial y of the line creates the changes in the voltage and in the current. Now let's differentiate each of these equations with respect to t and y. And remember what I told to you, that this is a primary wave propagation problem, and from physics classes we have learned that a wave changes in space with respect to time. Now if we differentiated these equations with respect to y, we will obtain the second partial of v with respect to a square partial square y, which gives us minus r times partial y I with respect to partial t minus l times second partial I with respect to partial I times partial t. Now we will do the same process for t. We will obtain the second partial v with respect to partial y square with partial y times partial t, which is equal minus r times partial y with respective partial t minus l times second partial I with respective partial t square. And this is for this equation, which represent this first section or partition, if you prefer. Now let's do the same process of differentiated for this another partition of this structure. First with respect to y, doing the differentiated we're gonna obtain the second partial I with respect to partial I with respect to partial y times partial t, which is equal minus d times partial v with respective to respective to partial t minus c times the second partial v with respective to partial t squared. Now let's differentiate it with respect to t, which will give us second partial I with respective to partial y squared, which is equal minus d times partial v with respective to partial t minus c times second partial v with respective to partial t times partial y. Okay, if you have a curiosity to see what we gonna do on the next video, because I don't wanna make this video longer, we're gonna combine these equations in order to eliminate variables, and this way we will obtain two differential equations that are gonna describe our transmission line. But we still a bit away of finish to find the characteristic impedance. So that's it. Thank you for following along.